A'udhu billahi minash shaitanir rajeem. Bismillahir rahmanir rahim. Dear students, assalamu alaikum. Today's our lecture is class 10, subject physics. The chapter we are doing, chapter number 12, geometrical optics. Topic of today's lecture is as we will try to solve problems 12.8 to 12.12, which are on page number 67. I repeat, class 10, subject physics, chapter 12 we are doing, and the name of the chapter is geometrical optics. Topic of today's lecture, we will try to solve problem 12.8 to 12.12, and these problems are on page number 67. Please open 10th class books, page number 67, and I'm going to start 12.8, problem number 12.8. This is a chapter we are doing, unit 12, geometry. The name of the chapter is geometrical optics. And today we will solve problem number 12.8, which is on page number 67 of 10th class. I read the statement of the numerical first. 12.8 statement. An object 4 centimeter high is placed at a distance of 12 centimeters from a convex lens of focal length 8 centimeters. Calculate the position and size of the image. Also state the nature of the image. I repeat, an object 4 centimeters high is placed at a distance of 12 centimeters from a convex lens of focal length 8 centimeters. The focal length of the convex lens is 8 centimeters. Calculate the position and the size of the image, also the nature of the image. First of all, I will write the given data, and you know object height is given to me HO, and object height is noted with HO, which is given to me 4 centimeters, and the object distance is noted with small p, which is also given to me 12 centimeters, and similarly focal length of the convex lens is also given to me 8 centimeters. Since it is not the mirror, it is the lenses. No, I'm talking about the lenses. So convex, in case of convex lens, the focal length will be positive. Okay. So in this numerical, I need to find out image distance, which is noted with Q, and image height, HI, and the third thing I will find nature of the image. Okay. I will use I told you when we discussed this, 1 over f is equal to 1 over p plus 1 over q. This is called the mirror formula, which holds for both for mirror and lenses. Now I am talking about lenses, convex lens. The formula will remain same as we discussed in convex mirror and concave mirror. We will use the same formula for in case of lenses. So my formula will not change; it will remain same whether they are lenses or whether they are mirror. Okay, but the only thing will change in case of convex lens. The focal length will be taken as positive. Okay, so 1 over the sign convention will vary, but the formula will not change, and the formula will be 1 over f is equal to 1 over p plus 1 over q. It is the formula. So again, I multiply both sides with PQF. Here I multiply PQF, 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 as I discussed in my earlier numericals. So many times I told you this, I multiplying both sides with PQF. So F will be cancelled in this case, P will be cancelled in this case, Q will be cancelled here. So what will be left? PQ, QF, and PF will be left. So since I want to find out the Q, so I will separate out Q. QF, if it is here plus, if it is go on the other side of the equation, it will be minus. So PQ minus QF is equal to PF. So I am going to take Q common because I want to separate out Q. So what is left in the brackets? P minus F is equal to PF. I repeat, I multiply this equation. This is called a mirror formula, which holds for both mirror or lenses. The formula will be remain same, while only things will change is the signs. Okay, sign will be changed. I multiply both sides, PQF here, PQF here, PQF here. So F will be cancelled with this F, P will be cancelled with this P, and Q will be cancelled with this Q. So what is left? PQ here, PQ left, QF and PF left. Okay. So what I want to find out Q, since I need to find out Q, so that's why I'm plus Q over here, QF here. If it is go on the other side of the equation, it will be minus QF. So taking Q common, so what is left in the bracket? P minus F. Since I want to find out, I want to separate out Q, so Q minus F will be, P minus F will be divided here. I'm just putting the values now. Value of P is 12. I show you now. The value of P is 12 and F is 8. Just plug in this formula. Value of P is small p is 12, which is object distance, and F is the focal length multiplied by 8. So P is again 12 and F is minus 8. So 12 multiplied by 8 is 96. 12 minus 8 is 4. So if you divide 96 divided by 4, you will get Q is 24 centimeter. One more thing which is required in this numerical is height of the image. How can I use this formula? HI over H naught is equal to Q by P. I have discussed this formula also in my previous lecture. HI is equal to Q by P multiplied by H naught. H naught you got to remember. H naught is the object height and HI is the image height. So Q by P multiplied by H naught. Just plugging the values. Value of Q is 24. I show you now. Value of Q, I just found it, 24 and P is 12. Value of Q is 24 and value of P is 12. So I'm just, and the height of the image is 4. I show you now. Height of the object is 4 centimeter. So this is given to me. I just plug in all the values, value of Q, which is 24 centimeter, and value of P, which is 12 centimeter, and H naught, height of the object, is also given to me in the numerical. So that's why I'm putting this value for this. So I get 8 centimeter. Height of the image is 8 centimeter. Image is formed is real, inverted, and magnified. What I what I'm saying is, why I'm saying magnified, you can see the object distance is 12 centimeter, but Q image distance is 24 centimeter. It is magnified. It is greater than the value of P, so it is magnified image. And the image is, since Q is positive, it is real, inverted, and magnified image will be formed. So my result will be Q I just found is 24 centimeter and HI is 8 centimeter with the height of the image, and the nature of the image is real, inverted, and magnified. So in this numerical, three things were required. Image distance Q I found 24 centimeter. Image height I just found is 8 centimeter. And the one more thing which is required here is nature of image. And my nature of image is real, inverted, and magnified. Three things were required in this numerical. So I found three things: Q, HI, and image, nature of image. So Q is 24 centimeter. Height of the image is 8 centimeter, and my image will be real, inverted, and magnified. Now I'm moving towards problem number 12.9. First of all, I read the problem 12.9 first. An object 10 centimeter height, its mean height of the object is 10 centimeter, is placed at a distance of 20 centimeter, its mean P is 20 centimeter from a concave lens. But when we discuss about mirror, I told you in concave mirror we have a positive F and Q, but in concave lens we have a F is negative. Okay, F will be taken as negative. Remember this. There are little bit difference in sign convention when we discuss mirror and lenses, but the formula will be same for both mirror and same. The formula is 1 over F is equal to 1 over P plus 1 over Q. This is called the mirror formula, which holds for both lenses and mirror. So image distance Q is required, image height is required, and nature of image is required. I will use this formula 1 over f is equal to 1 over p plus 1 over q. Again, I multiply pqf on both sides. So what is left? pq, remove this one, minus qf is equal to pf. As I discussed in my last numerical, I did the same thing. In my last numerical, in this numerical will be the same thing. Separate out q, pf minus pf, which is not going to be counted here. Just putting the values. Value of p is 20, and value of f is minus 15. As I told you, it is given to me. Value of p is 20 centimeters, and the focal length f is minus 15. I just putting the values in the formula. Q is equal to pfp minus f. So p value of p is 20, and value f is minus 15. Again, value of p is 20 minus formula, and value of f is minus 15. If you solve this, 15 multiplied by 20, you will get minus 300. So minus minus plus 20 plus 15, you will get 35. If you solve this, the value of q will be minus 8.57. Okay. So I use the formula H, the same formula as I discussed in the last numerical. Same formula used HI, our H naught is equal to Q by P. I separate out HI. HI means image height. So Q by P multiplied by H naught. Q is 8.57. I just found it. And value of P is 20. And H naught is 10. So object height is given to me 10 centimeters. You can see this object height is given to me 10 centimeters. Q I just found it. Q I just found it, which is 8.57, or P is 20. You know the value of P is 20. It's given to me. So I just plug in the values over here. So I will found image height is 4.28 centimeters. So image will be virtual, erect, and diminished. Why it is called diminished image? I just explain you. Well, P value is 20, and Q is now 8.57. It means it is a which negative sign show that the image is virtual, and erect and diminished means it is smaller than the object. That's why it is diminished image will be formed. So in this numerical, I found Q is minus 8.57, and negative sign show this is a virtual image. Okay, and diminished image because this is less than the size of the Q. Value of Q is less than the value of P. So it means this is the diminished image. This is not magnified image, the diminished. HI just found is 4.28 centimeters. And image form, these three things are required: Q, HI, and image nature of the image. Q is minus 8.57. I told you earlier on. I want to find out image Q, image height, HI, and nature of the image. So three things are found. Q is minus 8.57, and HI is 4.28, which is the image height, and image form is virtual, erect, and diminished. This is the end of the numerical 12.9. Now I'm moving towards numerical problem number 12.10. This is problem number 12.10 now. Problem number 12.10 is, I read the first of all, I read the numerical statement. 12.10, a convex lens of focal length 6 centimeters. Convex lens of focal length 6 centimeters is used to form a virtual image 3 times the size of the object. Virtual image 3 times the size of the object. Where must be the lens be placed? I want to find out object distance. Again, I repeat, our convex lens of focal length is 6 centimeters. It means it is a focal length. The focal length will be positive for the convex length, and concave length it will be focal length will be negative. But this is a convex lens. My focal length will be positive. F will be 6 centimeters plus 6 centimeters, and magnification is given to me 3. Okay. Object distance I want to find out, capital P. So I just put it focal length. Focal length f is 6 centimeters given. Magnification is noted with capital M, and it is also given to me 3. Object distance is we need to find out. So I will use the formula due to the virtual, since this is the virtual image, so Q will be negative. Okay. So and magnification, the formula is minus Q by P. Just put the magnification is 3. So if you minus Q will be, if you cross multiply, minus Q equals to 3 times P. So if you write the minus sign with this, it doesn't matter. So Q is equal to minus 3P. So I will use the formula 1 over F is equal to 1 over P plus 1 over Q. So this is the mirror formula which is hold for both mirror and lenses. So I am just putting the values. F is 6 centimeter. F I am going to put 6. And Q is minus 3P. You know, Q I just found is minus 3P. So minus plus minus. So minus minus plus minus. So 1 over 6 is equal to 1 over P minus 1 over 3P. Now my numerical is going to be continued. This is 1 by 6 is equal to take the LCM, and the LCM will be 3P. 3 minus 1 is 2. So cross multiply 3P, and 3 minus 1 is 2. 2 multiplied by 6 is 12. Okay. So 3 over here is multiply. If it is going on the other side, it will be divide 3 for the 12. So object distance will be 4 centimeters. So my result will be lens must be placed at a distance of 4 centimeters. Lens must be placed at a distance of 4 centimeters to get virtual image 3 times the size of the object. If we want the virtual image, which is 3 times the size of the object, the lens must be placed at 4 centimeters. Okay. I repeat this numerical again. In this numerical, 6 centimeters is my focal length is given to me. Magnification is also given to me, which is 3. And I want to find out the object where the lens is placed. P, I want to object distance is P. My formula for the virtual image, Q will be negative, taken as negative because it's a virtual image. So Q will be negative. Magnification formula is minus Q by P. I'm just putting the magnification formula is Q by P. But since it is a virtual image, so that's why I'm placing negative sign over here. Okay. So M is 3. I'm just putting 3 and then cross multiply. So my Q will be minus 3B. Then using this formula, since I want to find out P, so 1 over F is equal to 1 over P plus 1 over Q. This is called the mirror formula, which is holds for both lens and mirror. So I'm just putting the values. Focal length is 6 centimeter and Q is, I just found is minus 3P. So minus plus minus. So taking the LCM, 1 over 6 is equal to 1 over P minus 1 over 3P. If you take the LCM will be 3P minus 3P will be the LCM. So 3 minus 1 is 2. So 2 6 the 12. And if you cross multiply, 3P will be multiplied with 1. And 3 minus 1 is 2. 2 multiplied by 6 is 12. So 3P is equal to 12. So if 3 is multiplied here, if it is go on the other side, it will be divided 3 for the 12. It's mean in order to get the virtual image, 3 times the size of the object, the lens must be placed at a distance of 4 centimeters. Now this is the end of the numerical 12.10. Now I'm moving towards problem 12.11. Problem 12.11 is, I read the statement first. A ray of light from air is incident on a liquid surface at an angle of incidence 35 degrees. Calculate the angle of refraction of the refractive index of liquid is 1.25. Also calculate the angle of refraction is the refractive index of liquid is 1.25. Also calculate the critical angle between the liquid air interface. Okay. I repeat, a ray of light from air is incident on a liquid surface at an angle of incidence. So angle of incidence is denoted with I, small I. So angle of incidence is given to me 35 degrees. And refractive index is denoted with small n, which is also given to me 1.25. So in this numerical, I am required angle of refraction is denoted with small r, and critical angle is denoted with angle C, which is called a critical angle. Okay, these two things are required, and these two things were given. Angle of incidence is given to me, and refractive index, which is denoted with small n, is also given to me. So I need to find out angle of refraction, which is angle of R, and critical angle, angle C. So these two things are required. Now I use this formula. This is the formula. Refractive index, capital small n is equal to sine I over sine R. Sine I over sine R. Since sine incident angle is given to me, which is 35 degree, I show you now. Incident angle is 35 degree, and n is given to 1.25, I'm plugging the values in this formula. Angle n is 1 point, which is called a refractive index, and refractive index is given to be 1.25, and sine of angle of incidence is given to be 35. Just plug in the values and separate out sine 35 degree. Sine 35 sine 35, if you divide this one, sine 35 is 0.5736 and divide this 1.25, so you will get 0.459. Okay, so taking sine inverse on both sides, if you take sine inverse on this both sides, this sine inverse and this sine will be cancelled out. Sine r equals to sine inverse 0.459. So if you take sine inverse of 0.459, you get 27.31 degree. And also we want to find out the critical angle. I show you now. We want to find out the critical angle. That's why I use this formula. And is the index is equal to 1 over index of refraction is equal to 1 over sine of critical angle. So just separate out this one and 1.25 underneath of 1. 1 divided by 1.25, if you divide this, you will get 0.8. And taking sine inverse on both sides, so if you take sine inverse 0.8 with the help of calculator, you will find 53.13 degree, which is the critical angle. So we just found critical angle is 53.13 degree and the angle of refraction is 27.31 degree. These two things were required. I repeat, I'm repeating 12.11. First of all, I read the statement for you. A ray of light from air is incident on a liquid surface at an angle of incidence 35 degrees. Its mean angle of incidence is this small I, and this sign this sign is for angle. The angle of incidence is given me 35 degree, and refractive index is also given to me, which is not to be small n, which is also given to me 1.25. In this numerical, we are asked to find angle of refraction, which is denoted with small r, and critical angle, which is denoted with small c. So these two things are required in this numerical. So I use the formula. The angle of refraction, refractive index is equal to sine I over sine r. Okay, just plug in the values and solve it. Sine r, take the sine r over there, and 1.25 will be divided. So if you take sine 35 degree with the help of calculator, you will came to know it will be 0.5736, and sine and the value of n is 1.25. So since we want to find out the angle of reflection, so taking sine inverse on both sides. So sine inverse of 0.459, if you solve with the help of calculator, so value of sine inverse of 0.459 will be 27.37 degrees. So again, we since we want to find out the incidence critical angle, so a formula for to find the critical angle n is equal to 1 over sine of angle C. N value of n is 1.25 as you already know, and sine of angle of C. If you take this one on the cross multiplication, 1 divided by 1.25, it will be 0.8, and sine inverse of 0.8 is 53.13 degree. So my sine of refraction, angle of refraction is 27.31, and critical angle is 53.13 degree, which is my required result. Now I'm moving towards last numerical of this last numerical of this chapter, which is 12.12. After this, we have finished this numerical. This is the last numerical of this chapter. So I read the first of all, I read the statement for the 12.12, which is on page number 67 of 10th class textbook. The power of a convex lens is 5D. 5D means 5 diopter. But the power of the convex lens is 5D. 5D means 5 diopter. At what distance the object should be placed from the lens so that its real and 2 times larger image is formed. 2 times larger image is formed. First of all, I write the power, and you shouldn't be confused with small p. which is the object distance, and power is not with capital P. There is a small difference between small p is the object distance, and don't confuse yourself with the object distance and power. So power is not with capital P, which is 5D, 5 diopter, and magnification is also given to me, which is 2. Object distance, this is small p, this is not the capital P, this is small p. Whenever you find object distance, it's small p, it is not capital P. First of all, I use the formula for the power. Power is equal to 1 over f, 1 of the focal length. Since power is given to me, so I want to find out the focal length. So f will be 20 centimeter. If you put the values of 5 diopter, this is the unit of the power, diopter. So 1 over 5 is equal to 0.2 meter. This is, I found focal length in meter. But I want to find out, since the focal length, object distance, and q will be in centimeter, that's why I convert this meter into centimeter. And in centimeter, the value of focal length is 20 centimeter. Now I use the formula m is equal to magnification is equal to q by p. I use this formula for so many times. So m is given to me 2. So just cross multiply. Q is equal to 2p. Q equals to 2p. If you cross multiply this, the image will be 2p. Next, I use the formula 1 over x is equal to 1 over p plus 1 over q. This formula is holds for both mirror and lenses. So 1 over f is equal to 1 over p plus 1 over q. So you know the value of f focal length is 20 centimeter. I just found the value of focal length 20 centimeter, and q is found to be 2p. I'm just putting this value of f and value of q in the formula. 1 over f is equal to 1 over p plus 1 over q. Okay, so q is 2p and f is 20. So if you take the LCM of 2p and p, the LCM will be 2p. So the on the top 2 plus 1, 2 plus 1 is equal to 3, 1 over 20. If you cross multiply on both sides, 20 multiplied by 3 is 60. 2p multiplied by 1 is 2p. So this is the object distance. This is not the power, this is the object distance. So 2 is multiply here. If it is on the other side, it will be divided. So 60 divided by 2 is 30 centimeter. Okay, this is not power, this is the object distance. Object should be placed at 30 centimeter from the lens to get real and 2 times larger image. This is required in the numerical. At what distance object should be placed from the lens so that it's real and 2 times larger image form. So object must be placed at 3 centimeter from the lens to get real and 2 times larger image. If we want to get the 2 times larger image, the object must be placed at 30 centimeters from the lens. Okay. So this is the end of the numericals of this chapter. I repeat this numerical for you. Problem number 12.12. First of all, I give you that. I read the definition, statement of the numerical. The power of a convex lens is 5D, 5 diopter. The power unit is diopter. When we discuss when we read the chapter, when we discuss this topic, power of the lens, I told you the power of the lens is the unit of power of the lens is diopter. The power of the convex lens is 5 diopter. At what distance the object should be placed from the lens so that its real and 2 times larger image is formed. First of all, what is given to me? Power. Power is not with capital P, not small p. Of small p, the object distance, and power is not with capital P, which is the and the unit of the power is diopter. Okay. So magnification is also given to me 2 times. Object distance, we need to find out. This is small p. This is not the capital P. This is small p. Object distance is small p. Power is not the capital P. So first of all, I use the formula. So power is equal to 1 over f. Power is the reciprocal of the focal length, 1 over f. So if you separate out f, so power is given to me, which is 5. I just plug in the values 1 over 5. If you solve this, you will get the power. Focal length is 0.2 meter, which is in meter. But since focal length, object distance, and image distance always in centimeters, so that's why we convert this 0.2 into centimeter. So our focal length in centimeter will be 20. Magnification formula, as I use this formula so many times, so you should know very well now. M is equal to Q by P. So M is 2, M is value, just putting the value 2. If we cross multiply, the image will be Q equals to 2 times P. So value of F I'm going to put, and Q equals to 2P I'm going to put in the formula. 1 over F is equal to 1 over P plus 1 over Q. You know that for F is focal length is 20 centimeters, I just found, and the Q is 2 times P. I'm just putting this Q is equal to 2P. So if you take the LCM of P and 2P, it will be 2P. So 2 plus 1, so it will be 3. So if you cross multiply, so 2P multiplied by 1 is 2P, 20 multiplied by 3 is 60. So object distance is 30 centimeter. If you solve this 60 divided by 2, it is 30 centimeter. So our result will be, if we want to find out the get the real and 2 times larger image, the object must be placed at a distance of 30 centimeter. This is our result. So the student, this is the end of the numericals of chapter number 12. So if you have any question regarding today's numericals, please feel free to ask a question. I'm here. I'm waiting for your question. Thank you. Yes, student. If you have any questions, please let me know. Daniel, please unmute your mic and ask questions. If you have any question regarding today's topic, please let me know. If you didn't understand any part of the numericals, please let me know so that I can repeat for you. Yes, Daniel. Feel free to ask questions. Okay, thank you.